Yeah, I'll go by Luke's Green on internet. My name is Lucas, and I'm currently finishing my PhD in applied mathematics. It's actually applied to biosciences, but nonetheless, I've been very interested in several subfields of mathematics, including algebra and cryptography, right? So I've noticed that many people coming from the field of computer science aren't really familiar with certain basic algebraic concepts, and especially when some mad mathematicians invent these protocols and these
Yeah.
rhythms such as KZG commitments, right? So I thought, let's digest this a little bit, right? Make it easy for newcomers, and yeah. So this session is all about that. It's all about the
Cool, brother.
algebraic background and the algorithm itself, right? So yeah, it's going to be a heavy session because there's going to be a lot of algebra. Nonetheless, everything's written down. I'm going to share the link of the repository once we're done with the session, and yeah, I'm just gonna go, swiftly over the concepts, and then we're gonna go straight to the algorithm because I think that is what's most interesting, right? So, everything clear up until now?
Everything clear.
Okay, so a small remark I wanted to do is that originally, right about computational hardness and cryptographic groups. But since that is very well explained in the Moon Math manual, I'll skip it, okay, because it's not so essential to grasp the basics of KZG, right? So it's a little bit less content, okay, but let's go into it. So something I get usually asked from people that are not really familiar with mathematics is that what is algebra, right? So many people that have done, understand that algebra is like treating equations and finding solutions. Well, not quite so, actually. See, algebra is a field that studies mathematical structures and how they interact with themselves, right? So, if we go really back to the foundations of mathematics, everything is set theory. We have a set of things, like we have a box full of things, and they behave a certain way, they have certain properties, right? You can relate them with certain operations, right? So the most elemental mathematical object are numbers, and as you may know, numbers come in sets, right? So here's a tiny introduction regarding that. See, the most basic set, it would be the set of natural numbers, which is represented by these fancy n, right? That would be 1, 2, 3, 4, 5, and so on, right? These are constructed using a certain set theoretic logic and the Zermelo-Fraenkel axioms, which I'm not going to explain. But yeah, once we have the numbers, we can keep asking ourselves questions regarding operations. And okay, does such a number exist such that I add it to number one and I get zero, and so on, right? And when you do those questions, you actually are constructing new sets of numbers. For example, the sets of integers, which get the negative numbers that, 1 plus minus 1 gets 0, 2 and minus 2 gets 0, and so on, right? So you are actually you build yourselves new sets of numbers to fulfill certain needs. If we keep doing that, we get the rational numbers, right? And in the end, we also get the irrational numbers, sorry, the real numbers. I'll have to go back because I clicked the notebook. We get the real numbers, etc. Oh, sorry, here. So we even get the complex numbers, which are an extension itself from the real numbers that come from the need of finding the roots of a quadratic equation, right? But so there are different sets of numbers. When it comes to KZG commitment schemes and cryptography, usually we will only focus on the set of integers, okay? There is certain integers that have special properties, such as the prime numbers. See, a prime number, well, to be more formal, is a natural number that has the following properties. It is greater than 1 and is only divisible by itself and 1. See, a number is divisible by another number if their division is an integer. So for example, if you have 3 divided by 4, 3/4 is not an integer, right? So 3 is not divisible by 4. But if you have, for example, 6 divided by 3, 6/3 is 2, and that is an integer, right? So 6 is divisible by 3. Okay, so we use this fancy letter P to denote the set of prime numbers. From this point on, whenever we have a number, we can evaluate if two numbers are coprime. What does that mean? That means that they do not share a factor besides 1. In other words, their greatest common divisor is 1. This will come in handy once we start building these algebraic structures that lead us towards the foundations of
Nice.
KZG. So for example, 4 and 9 are coprime trivially, right? So because 4 is 2 squared and 9 is 3 squared, right? So they don't share any factors. But 4 and 8 are not, because 4 has 2 squared and 8 is 2 to the cube. So there is the 2 squared here that is shared between them, right? So this will be a very nice property that we will check in order to work with some cyclic groups. Okay. So next step, well, I guess until now this is something that you guys are not really familiar with, but you might have heard of it. Another thing will come in handy when looking into KZG commitment schemes is modular arithmetic. So it's as you know, it's a system of arithmetic for integers where numbers wrap around, right? So for example, if you're in modular arithmetic of base 5, uh, once your number reaches 4 and you add one more, it's not 5, it's 0 again, right? It wraps around. So for you solidity programmers, it doesn't sound familiar with the concept of overflow and underflow? See, actually, a solidity unsigned integer 256 type is a positive integer defined on modular arithmetic of modulus 2 to the power 256. That's why this number
Wow.
equals 0, right? It wraps around. So yeah, as I said, modulus 5, let's say 4 plus 3 is 7, but since we haven't wrapped around, it's actually 2, right? Yeah, this symbol is equivalent, right? Because obviously 7 is not equal to 2, but it's equivalent under these rules of operations, right? So the same happens with product, with multiplication. The funny thing about this is that we naturally certain properties arise, right? So if we do this with 5, we see the only possible numbers that will be 0, 1, 2, 3, and 4, right? So if we're doing this with a number n, we have the set of numbers that go from 2 to n minus 1, right? So this set, you can actually put a fancy name on it. Set underscore n, or well, in my case, I like to denote it this way, but the Moon Math Manual uses it this way. And since I will highly recommend you guys read that book after this, let's keep it with this notation. Okay. So yeah, these concepts give rise to what is called equivalence classes. So as we mentioned earlier, 5, in modular 5, 7 and 2 are equivalent in such sense. And the same thing, for example, the number 12 and the number 7 and number 2 are also equivalent because the remainder will always be 2 when dividing by 5. So this is something we deal with every day in our lives. So when you look at the clock, right? If it's 1 p.m., what time is it in a digital clock? It's
13?
13.
Yes.
Yeah, so 13 is equivalent to 1 because we're actually doing modular arithmetic in base 12, right? 13 is equivalent to 1 under modulus 12.
Really nice, bro.
Same thing, 0 is equal to 12, and same thing, 12 is equal to 24 under these arithmetic rules, right? Cool. So yeah, up until now, I guess you guys must have heard of it and worked with this. Okay, but these ingredients will make it easier for us to define the most basic algebraic structure. which we're going to jump in right now. Okay. So till now, do you guys have any questions? Should I check out the chat? The chat.
N-
Let me check out
no
the chat.
questions so far. Let's go. Let's keep going.
Oh, okay. Okay. So cool thing. So yeah, let's jump into some basic algebraic structures. Um, for those that didn't like my definition of algebra earlier regarding the boxes and the things and the operations with the things within the boxes, I always like to mention a class in object-oriented programming, and we have some methods that manipulate the class instances. That is actually algebra, right? So if you think it that way, if you're from a computer science background, I think you will not struggle. Okay, so let's start with abelian groups. This is just a fancy way of saying commutative groups. And what does this mean? This means we have a set G that has certain elements. It can have a finite amount of elements, infinite amount of elements, doesn't matter. And we have a binary operation. I put this symbol because if I put that plus, most people get confused and think about addition. It doesn't have to be addition, okay? But so I put this weird symbol. This is just an operation that takes two elements of G and returns another element. So these properties, if these properties are hold, we have a commutative group or abelian group. So the first one is closure. That if we take two elements D of the set G, we apply the operation, the result is also of the set G. So for example, imagine our set G is the set of all drinks that you can have. All drinks, right? Orange juice, gin, uh, I don't know, Sprite, whatever. So imagine you take Sprite and you take gin, and the operation, this means mixing the drinks together. What do you get? You get another drink, which is Sprite and gin, right? But it still belongs to the set of drinks, right? It still is inside this set G. So we would say that the operation of mixing respects the property of closure, right? Does it make sense?
Yeah, actually makes sense, bro. You are better, much better teacher than my teachers at the school, bro.
Yeah, most people at university don't like these kind of weird examples, but I do enjoy them a lot. So yeah, associativity means that it doesn't matter which order you apply the operations. So you can, for example, let's go back to example of drinks. So we have Sprite, we have gin, and then we have, I don't know, lemon juice. It doesn't matter the order, whether I mix Sprite first with the gin and then I mix the lemon juice, or either if I mix the lemon juice, the gin, and then the Sprite, it doesn't matter. The outcome will be always the same. Another drink. A terrible one for sure, but it's still a drink, right? So the associativity property held. Okay, identity element. This one, we gotta stretch the example a little bit, but bear with me, it's gonna be worth it. So the identity element means that there exists an element E, also from the set G, such that for every other element A from G, well, and E itself, if you apply the operation, you get the element A back. E is the identity element, sometimes also denoted by a bold one. So in our example of drinks, right? Imagine you have orange juice and our identity element will be water. You mix orange juice with water. What do you get back? You get orange juice back. Still watery, right? I know I get it. The example is not the best, but you get the point, right? It's not another drink. It's still orange juice, right? If we think about addition, for example, in addition, if you take any number and you add it to number zero, what do you get back? That any other number that you had previously, right? So that is the identity element. Inverse element. Inverse element would be an element by applying the operation, you get back the identity. So in this case, for the drinks example, I do not think of a drink that you can add to another drink to get water back, to be honest. But yeah, see, our operation of mixing drinks would not respect the inverse element, right? But in this case, inverse elements for integers would be the negative integers. For example, the inverse of 1 would be -1 because you get 0 back. which is the identity. And finally, you have commutativity, which means that the order of operations doesn't matter. So it doesn't matter if you, for example, orange juice with gin, then gin with orange juice is the same. Okay, so if we think about object-oriented programming, it's basically you have a class with a method, it takes two instances of the class, and returns another instance of the same class. So the class is the set, the method is the binary operation, and the instances are elements of the set. Okay. So here we have more examples of Abelian groups. I'm not going to go through them because you can read that on your own. But uh, keep keep in mind the example of the drinks because they're quite intuitive, I think. Okay, so yeah, if the commutativity properties is not present in the operation, for example, if this doesn't hold, then we don't have an abelian group. We just have a group because abelian implies commutative. So now I got a question. Can you think of an example of a group that is a group but not abelian, like a set, an operation that has all of these properties, but doesn't have commutativity?
I don't know if we can talk about food because I guess
Well, you can go as dumb as you want. Whatever is. Mathematics is all about abstraction.
you have different kinds of foods, but they're not, not all of them belong to the same class. I would say, So when grouping those, I don't know what will be the result.
Uh, yeah, it's pretty hard to find, an example out of the get-go that is a, real-world example. But for example, if we think about mathematical objects, uh, are you familiar with matrices?
Yes, yes.
A matrix. Okay. So what happens if you take the set of n by n matrices? It doesn't matter the size, and you take matrix product. Tell me, is it the same multiplying matrix A by matrix B than multiplying matrix B by matrix A?
I have no idea, to be honest, brother.
Well, the answer is not always. It's not always the same. The matrix product is not commutative, right? So that would be one example in which you have an
Nice.
operation defined, in this case of our matrices, where the order of the elements you are multiplying um, is important because they're not the same. It's not the same A times B. It's not the same that B times A. Okay. So this would be one mathematical example. So once we have the definition of abelian groups, see the examples we gave are infinite. The integer, pretty much the set of drinks you have in the planet is almost infinite. Obviously not. But see, when the set is not infinite, it has a finite amount of elements, then we call it finite group, finite abelian group to be more precise, right? And the number of elements on the group is called the order of the group, and you can denote it with two bars like this, right? So do you remember the set of integers in modular 5 arithmetic? 0, 1, 2, 3, 4.
Yes.
This with the binary operation plus under modular arithmetic 5 would be a finite group. If it wasn't under modulo 5, then it would not be a finite group. Why? Because 2 plus 3, for example, would be 5, and 5 is not in the set unless we do the modulo, right? If we do the modulo, 5 turns into 0, and that is in the set, okay? So make sure that you have all the properties right so you can give the proper name. Okay, so all groups that come from these modular arithmetic and you apply the modular sum, they are finite abelian groups of order n. So in a similar fashion, you have also cyclic groups. Cyclic group is a group that can be generated by a single element, which is trivially called generator, right? See, for example, the integers, you can create all integers with number 1. How would you just take number 1 and add that number to itself all the time? 1 plus 1 is 2, 1 plus 1 is 3, and so on. You can do that until you get tired of, because that's the way you get all the integers. And if you take the inverse of 1, which is -1, and keep adding it to itself, you get all the negatives, right? So that is the way you generate the integers. If you're in the modular 5 arithmetic, you can get, you have all the 4 generators. For example, let's grab number 2. 2 plus 2 is 4. 4 is in this set. 2 plus 2 plus 2 is 6, which is 1 under modular arithmetic, which is also in this set. If you keep doing that, you get a number 3 and you get 0, which is 5, right? So you have recovered the whole set only with the generator and your operation, right? This is called cyclic group. And this is something that is used every day in cryptography. You'll see in our application in the KZG Polynomial Commitment. Here's a tiny exercise you can try out to get the generators. If you do not have a prime base, then not all your elements are generators. For example, under modulo 12, the generators are only 1, 5, 7, and 11. Why? Let's take number 2. If we add 2 to itself, we get 4. We add it again, we get 6. We add it again, we get 8. Then we get 10. Then we get 12, which is 0. And then we add it again, and we get 2 back. So we made a cycle, but we didn't get any of the odd numbers. So we cannot recover the whole set only with the number 2, right? In fact, all elements of the set which are not coprime with the modular base, they will not be generators. Do you remember coprime numbers we just mentioned minutes earlier? Here it comes in handy to find out what can we use as a generator. Cool. So yeah, now things start to get tough, okay? Exponential map. So let's say we have a finite cyclic group, which is something we just learned. So we have a set with this operation, and it has an order. And since it's cyclic, it has a generator, okay? Exponential map is a function that takes an integer from this modular group and returns the element of the group that is generated by this operation. Okay, this operation doesn't mean exactly exponentiation. Okay, it means basically applying a times the operation of the group on the generator. Okay, to understand it better, let's take our modular 5, uh, modular 5 finite cyclic group with modular 5 arithmetics. Okay, so we'll take a generator. Let's take number 2. It doesn't matter. We can take any number of the set, and we test this operation. Okay, let's test 2 times a under modular 5. This will be our exponential map. Okay, so when we have 0, we get 0 back on the group. If we have 1, we get 2 on the group. We have 2, we get 4. With 3, we get 6, which is equivalent to 1. With 4, we get 8, which is equivalent to 3. If you look on the right side, we have recovered the whole set just doing this, just applying our map to the integer set of base n, where n is the degree of our, degree not, our order of our group. So the cool thing about this is that we will use this later to do something that is called evaluation of the exponent, right? So until now, we have a way of going to one group of numbers to another arbitrary group with a single operation, as long as it is cyclic and finite. Okay. Does it make sense until now?
Yeah, brother, makes sense. I'm not the best at math, but I'm loving it.
Oh, cool is that you'll have time to read this on your own pace because it's a lot to digest. I know
Awesome.
that.
I'm gonna invite everyone to
Oh,
speak, so if everyone has questions during the talk, they can ask. Okay?
yes, please, and please interrupt me if there's any questions because I'll be more than pleased to answer.
Awesome.
Okay, cool. So this is one example of exponential map. Imagine now we have instead of have a group that is this is the multiplicative group of modular 7, and we use the multiplication under modulo 7. This is of order 6, so we can go to the integers of modulo 6 to this group using the generator 3, and we use the power A. And you can see here we recover all the numbers. One fantastic property is that the neutral element of this set, which is the 0, it maps directly to the neutral element to this set, which is the 1. See here? Here the neutral element was 0 and it mapped directly. So this is a very, very nice property that will come in handy for KZG polynomial commitments. Yeah. You can use this notation because it's the multiplicative group. Okay, so yeah, as I mentioned, this will help us to do calculations in the exponent. This is a silly example, but you will see one with polynomials later on that will make much more sense. So if you want to multiply 5 times 3 times 6 in modular 7, you can do it like brute force. You multiply it, it's 90, and then you find the remainder by 7 and it's 6, or in the exponent. So you turn this 5 into 3 to the power of 5. Why? Because see, 5 is 3 to the power of 5 here. And you do that with 6, with 3 as well. Then you put them together, add this, which gives you 9 in modular 6 arithmetics, because it's the base of this group. And we get 3 cubed. And we compute this as 27, which in modular 7 is 6. So it's basically you jump from this group to this one to make computations easier, and then you jump back. Okay, this is a very nice property. When the group is really big and it has a lot of elements, doing these jumps makes everything quicker computationally. Okay. Okay, this was heavy stuff. Any questions?
No questions from me. I don't know if you guys have questions, please just drop them in the chat.
Yeah, I'll be changing on the Discord channel to check out questions. Okay, so yeah, let's jump to pairings. Pairings is something we're going to use to verify our proof. You'll see later on. So a pairing map takes elements from a group 1 and from a group 2 and returns an element of another group. So the pairing E, let's call it E, okay, takes a pair AB such that A belongs to G1 and B belongs to G2. And if it has these two properties, it is suitable for our proof verification in KZG. So it has to be bilinear, which means that you can take the operation out, right? So you can do this separation. It doesn't matter if it's on the first argument or on the second. And it is said to be non-degenerate if we get the neutral element of the landing group, then it has to follow that either G1 or G2 are the neutral elements of their group. So the easy example is you take a set of integers with addition. You define the pairing as multiplication. So you can do the distribution law, right? So that means it's bilinear. And if you get that the pairing gives you 0, either one of the arguments, one or both of the arguments has to be 0, right? So a question I usually make is that, can you think of another example of pairing? This is a nice question because if you know a little bit of elliptic curves, you probably have one answer in mind, right? But since we're not doing elliptic curves, I'd rather skip this, okay? And keep going. I see no questions for now, okay? So I'll keep going, okay? Cool. For now, we have seen commutative groups, finite groups, cyclic groups, and groups that are finite, cyclic, commutative that come from integer arithmetic in modular algebra. And now let's jump into rings, okay? Rings, there's many definitions for rings, okay? But I love to define rings as a tuple that takes set, one bilinear operation and another bilinear operation, and it satisfies the following properties. R and the first operation is an abelian group. So, for example, set of integers with the addition, that is already a group. And then for the other operation, it has to follow that there is commutativity, associativity, distributivity, and and an identity element. So the best example for this is integers with addition and multiplication, because all of these properties hold, as I mentioned here. Notice that for convenience, we can denote that the neutral element for the identity element for the first operation is a bold 0, and the identity element for the second operation is a bold 1, as to reminiscence the identity elements of the sum and multiplication. Cool. Rings can give rise to yet another algebraic structure that is more complete, which are fields. Okay, a field can be defined in a similar manner. A field is again tuple of a set of two operations, binary operations, where this is already a ring, and it is a field if and only if for every element of the set minus the 0, there exists an inverse, such as when applying the second operation, you get the identity. So think about multiplication, okay? So the set of integers is a field. The set of integers is not a field, but a ring. Why? Because although you have the multiplication, you do not have any inverse. Okay, so for example, number 2 is an integer, and you have to multiply it to another number to get number 1, which is the identity element. But the inverse of 2 doesn't exist as an integer. That's why we created the rational numbers, because thanks to the rational numbers, we have fractions, and fractions arise because we are trying to look for the inverse elements of integers. So for example, the inverse of 2 in the rational numbers is 1/2. See? So all these number sets that you can learn about, they actually come as extensions of each other, because they wanted to complete the sets regarding the operations we put on them. Okay, so this is the general definition of fields, but then there is a very special field type that we're going to work with right now, which are Galois fields. The name comes in honor to Évariste Galois, which is a French mathematician, died very young. He was a pioneer in this field, and Galois fields are basically finite fields. That means it's a field. That means a finite set that is an abelian group with respect to the first operation, and the ring with respect of the second, and it also has inverse elements. Cool thing here is that you guys already know example of Galois fields, which is any any modular arithmetic of base prime number gives rise to a Galois field. Why does it have to be a prime number? Well, if it's not a prime number, not every number has an inverse, okay? So to demonstrate this, let's take the integers of modular 6 arithmetic. We take the binary operation product under modulo 6, and it implicitly has the addition under modulo 6. If we construct a product table, this is what we get. So 0 times 0 is 0. As you see, we get a row and column full of zeros. And then we start multiplying elements. 1 times 1 is 1, see, 2, 3. Note that, for example, 3 times 3 is 9. Under modular arithmetic is 3. Okay? And 4 and 5 and so on. See that there are rows and columns that do not have a 1. For example, row number 4, or row number 3, or row number 2. That means that these numbers 2, 3, and 4 do not have an inverse inside these set. Therefore, it's impossible for it to be a Galois field. It will remain a ring. Do you notice something particular? What do 2, 3, and 4 have in common? Well, the property that they have in common is that they share a prime factor with 6. So 2 times 3 is 6, 3 times 2 is 6, and 4 is 2 squared, right? So it shares the 2 with the 6, because 2 times 3 is 6, right? Do you remember coprimes? these are not coprimes. But what about 1 and 5? 1 and 5 are coprimes, and therefore they do have an inverse. So see that the property of coprimes allows us to notice which elements within a, a ring have inverse and which do not have inverse. If we didn't have if it wasn't modular 6 arithmetic and it was a prime number, I assure you every single element would have their inverse. And you can do that at home. It's easy to just make this table and make all the products, and you will notice there will be a one in at least one entry of sorry, not in at least, in exactly one entry of numbers. Okay, cool. So now we have seen certain algebraic properties. So it's basically checking that the operations we're doing on our set have certain norms and they are fulfilled. So cool thing now is that we can jump into polynomials. And this is, I swear, this is the last part of the theory before jumping into the algorithmics itself. So please bear
Awesome.
with me because the fun thing is about to begin. Okay, so yeah, basically polynomials, right? You might be familiar from school about quadratic equations, cubic equations, and so on, right? And you may say, okay, I know what a polynomial is. It's pretty simple. Yeah, I mean, you are familiar with polynomials that live in the field of real numbers. Okay, why is that? Well, because if someone would ask you, okay, can you find me the roots of this quadratic equation? Remember that there are three types. It has one double root, it has two unique roots, or it has no real roots. All these things actually come from algebra. So what's the hassle? Why? Why is it so important? Where does the polynomial live? The answer is the following. And let's illustrate this with an example. Let's take this, x squared minus 2. If you remember from school, well, let's take this polynomial and solve it. Like, let's make it equal to 0 and find the roots. You'll see that you'll get a square root of 2 and minus square root of 2. Why? Because you can do this. You can define it this way, and if you plug in root of 2 or minus root of 2 and x, you will do the product and you will get 0. Okay, but what happens if this polynomial lives in the finite field of modular 5? Again, to recap, finite field of modular 5, what does that mean? That's a prime field. That means the elements that live in the set are 0, 1, 2, 3, 4. We have an addition, which is sum in modular 5. We have a product, which is multiplication in modular 5. Everyone has inverse in multiplication and in addition. There is a neutral element for addition, which is the 0. There's a neutral element for multiplication, which is the 1, and so on, right? So it is well behaved. Okay, what happens here? First question, does this polynomial belong to this field? The answer is yes. The coefficients, 1, minus 2, they exist here. But does this have roots? No, because plus minus root 2, they do not belong to this set because they are irrational numbers, right? So they do not belong to the set. That means mm, this polynomial is irreducible in this field, but in the real numbers you can factor it into this product, right? I know it can be weird because it's another way of thinking about mathematics, but these are very nice properties because you actually realize that the way we work with numbers and the way we compute things depend on which sets of numbers we are using and how the operations are defined. Okay, another fancy example is the polynomial x squared plus 1. So if we're in the real numbers, we factor it this way, where I is the imaginary unit. And we would say, okay, it has no real roots because there is no real number that makes this go to 0 because I is the imaginary unit. It doesn't exist in the real numbers. Okay. But if we are in the complex field, then it has two roots, plus minus I, because this number does exist in the complex field because it's the field of complex numbers. If we're working in modular 5, the prime field of 5, modular 5 arithmetic, this polynomial has two roots, 2 and 3. And you may ask, why? Where do 2 and 3 come from? Well, that's so weird. Well, remember, we're in modular 5 arithmetic. So if we take this, I propose you this factorization, right? Let's develop it. So x times x squared, minus 2x, minus 3x, minus 2 times minus 3 is plus 6. We add terms like terms together. And if we perform modulo 5, minus 5 obviously goes away because it belongs to the remainder class of 0, because 5 times minus 1 is minus 5, and the remainder is 0. So this vanishes. And 6 belongs to the equivalence class of 1, because 6 divided by 5 is 1, and the remainder is 1. So we get x squared plus 1. See, so the way we factor polynomials also changes depending on where these polynomials live. I know this is very hard to do by hand if you're not experienced with, but we have very nice mathematical software called sagemath, which we're going to use today, that makes things very easy in this way. Cool. So if you've survived until now, congrats, because this has been a hell of a ride. Most algebra courses, just to cover this, they spend at least one semester. We spent 30 minutes, so congrats.
That's pretty cool.
uh, yeah, you guys will have this for your own selves, so don't worry about it. Okay, so let's jump into the algorithm, which is what we are interested about. So KZG, K-Zabaruka-Goldberg commitments. See, this is a commitment scheme, and that allows to commit to a polynomial, right? This is a polynomial of a degree t, where the polynomial lives in a prime field. Okay. Remember, to commit means that you prove that you know this polynomial without revealing it. So it's pretty tied to zero knowledge protocols, right? Think of it as a sealed envelope that contains certain information. So, if in order for a KZG commitment to work, we have several steps. The first one will be the setup step. Okay, setup phase, you only have to do it once, but it is the most crucial part, I would say. So you will take your ingredients to make your commitment scheme. So we'll take a Galois field, a prime field, okay? We'll define a maximum degree t for the polynomials that we'll be working with. It is mandatory that the maximum degree is strictly lower than the prime number you're choosing. Now, I put a remark here for you purists out there. If you want to do this properly, you must choose a prime number that fulfills k bits of security that you want to establish for your protocol. Okay. So if you want 128 bits of security, the prime number must lie between 2 to 128 and 2 to 129, right? Don't worry about this. This is information that you may need if you want to work on this. But for our example, you will see that we will choose very low amount of security bits because my laptop is not okay, and I don't want it to burn down. Cool. Next step is to define the generator of the finite, the prime field. Remember, a generator, if you have a cyclic group, and since we're in a prime field, obviously we have a cyclic group, is an element that allows us to get every single element of the prime field in this case. And then we need to compute two groups, G and GT, that have the same generator. We'll need to define a pairing that takes one and another element of G and gives you a result from the group G under T. It has to be bilinear and non-degenerate. So here's the step where if you're reading this at home later, you can go back and check out the definitions to understand what is happening. Cool. Then a trusted party picks a random alpha from the multiplicative subgroup and computes the public parameters. So the public parameters are a set of numbers. That is the generator to the power of a, the generator to the power of a squared, and so on until you reach generator to the power of a to the power of t, where t, remember, is the maximum degree. Once you have these public parameters, you can publish it publicly, right? And then the trusted party will have to delete alpha. Alpha is usually known as a toxic waste. Okay, so because if you don't delete it, you can tamper the protocol, and I'll show you an applied case of tampering a proof. Cool thing is that the trusted party doesn't have to be one person. It can be several people. It can be a multi-party computational scheme. Okay, so you can add layers to this. We're just covering the most basic case. Okay, now we have the ingredients, which is basically public parameters and all these ingredients that we were gonna base our polynomials on, and we can jump to the commitment phase. So in the commitment phase, I want to commit a polynomial where this polynomial belongs to the prime field. So we compute the commitment C as follows. We take the generator and raise it to the power of the polynomial evaluated on the secret parameter alpha. So if you've been listening until now, you might notice that alpha is unknown because the trusted party has deleted it. Well, thanks to the public parameters and doing some operations, we can see that we only using the public parameters and our coefficients, we can compute the commitment. You have here the proof. So we do this operation and we get the commitment. The commitment will be a number. And we send this commitment to the verifier. In this step, the verifier will enter the opening phase and will ask us to open the commitment to a random point of the prime field. The verifier chooses a random point and says, okay, I want you to evaluate your polynomial on this point and commit your result so that he can verify later that the polynomial that you claim to have is actually the polynomial and not some random information. So in the opening phase, the verifier has to form the opening triplet. That is the point specified by the verifier, the evaluation of the polynomial on the point, and the commitment of the proof polynomial. So what is that? What is this commitment? Because the first two elements are straightforward to get, but what is this? Well, this commitment is the generator to the power of another polynomial evaluated on alpha. And this polynomial you constructed from your original polynomial and the point S. To do that, we'll do some algebra. We'll use some algebraic properties. We get a polynomial from the field. We subtract the evaluation of the point. We know that S is one of the roots. That means we can factor it this way. And the proof polynomial will have degree t minus 1. And given that this equality holds, we can compute the proof polynomial as the division between our original polynomial minus the evaluation divided by x minus s, okay? Once we have this is straightforward with sagemath, you will see. We compute this commitment, which is raising this to g to the alpha, using the same trick of the public parameters. Once we have that, we send the opening triplet to the verifier. Finally, the verifier has to verify. And to do that, it has the following information: the public parameters, the first commitment, and the opening triplet. So they will use the pairing that is bilinear and non-degenerate to prove that you actually know this by means of this information without revealing what this polynomial actually is. How do they do that? Well, if you attempted to do it like raw, you will see that you would get this expression, but you would still need to know alpha. And remember, we are supposed to delete alpha. But if we used the bilinear and non-degenerate pairing, we only have to prove this. Why? Because if we take the bilinear pairing applied to the commitment and the generator, we perform some operations thanks to the properties of the pairing, which I'm not going to stop explaining them because it's out of the scope of the protocol. We'll get this expression. And as you see, the verifier has this commitment. This is present in the public parameters. This is easy to compute because we both know G and S. This again is easy to compute because we know G and we know obviously we know the pairing. And this, we know it as well because it's also part of the opening triad here. We have it here as our data, right? So if we compute this and both sides are equal, we have proven that we know a polynomial without revealing the polynomial. This is the raw implementation of KZG commitment schemes. So I know it's a lot of words, a lot of math, but let's go to fun part. Let's do the implementation, okay? So
Awesome.
let's do it step by step. This is a software called sagemath. It's also a Python library. It's very, very good to work with algebraic structures, to work with elliptic curves. If you want to play around with it, please feel free to download this notebook and execute commands and read documentation. It's really, really, it's a really strong software, and it's open source and free. Okay, cool. Let's do it again. Setup. Let's take a prime for making our prime field. Let's take a maximum degree of polynomials. And for the sake of simplicity, these groups are going to be also our prime field, but just because it's simpler. It's less secure because usually these groups are elliptic curve groups, which I did not explain and will not explain because that is way too hard, I think. But bear with me if you're interested in the topic. There are other constructions that make this protocol even stronger. Okay, so let's generate a safe random prime. Here I have a small algorithm to generate our prime with k bits of security. Let's choose 16 bits and evaluate this. Cool. Our random prime is 46,919. It's a pretty big number, right? So our field will have that many elements. It's not like 5 or 7 or 11. No, it's a big number. Usually here you would put a bigger number, 256 or something like that, right? But since my computer is not too beefy, let's stick to 16, which gives us
Awesome.
a fair big amount of number. Cool, let's define a prime field. That's how you define. GF is Galois field. That's how you define a prime field in sagemath. And let's generate a random t so that t is lower than our prime number. Cool. And let's take our generator. The generator will be 11. Nice. Let's define the pairing. Our pairing will be just the multiplication under modular arithmetic. Here I messed up because this was part of a actual example, but worry not. I'll write this better. So yeah, we have our pairing, we have our generator, our prime field, our maximum degree. Now let's take our alpha. We have to play we have to be the trusted party this time, but this is done by someone else or multi-party computation. Cool. Now we have an alpha. I'm not showing it for the sake of mystery, but we know our alpha. And let's compute the public parameters. I have made a function here that computes the public parameters, just as it was explained in the math. And I'll showcase you the first 100 elements of the public parameter set. They're just numbers, as you can see. Okay. Um, yeah. Do not forget, we should delete alpha. I'm not going to do it because we're going to tamper a proof later. Okay. Cool. Let's do commitment. To make this fun, and to explain why it is important to commit a polynomial, see, we can encode a message into coordinates, and these coordinates, we can encode them as a polynomial. So you're actually committing a message, a string.
Awesome.
We're using Reed-Solomon encoding. I'm not going to explain it because it's out of scope, but I'm just using it, for illustration. We turn a message into coordinates with this function I wrote, and I'm going to encode hello Zep. That will be our message. And hello Zep is encoded as these coordinates. Now, we have to construct a polynomial that passes through all of these points. To do that, we use the Euler-Lagrange method. which is implemented in sagemath. It's just a Lagrange interpolating polynomial. And we do that. We define the polynomial ring. Okay, here we have our polynomial ring x over finite field of our prime size. And then we get the interpolating polynomial. So this is our polynomial we want to commit that actually encodes our message, hello Zep. Cool. And now we will evaluate it on the exponent to get our commitment. I wrote here a function, so you guys do not have to go back to the math. And we write the commitment. Boom. And that's the commitment. This
Awesome.
number represents that we know an evaluation of our polynomial on alpha. And we raised it to the power of g. This is our commitment. And now we send this to the verifier. At this point, the verifier will ask us to evaluate the polynomial at a random point s. So the verifier chooses a random point. Okay, this. 30,604. This is absolutely random. I had no clue what this number was going to be. Now we evaluate our polynomial on S. Perfect. And next we compute the proof polynomial. Do you remember? It's our polynomial minus the evaluation divided by x minus s. And we get this polynomial. Notice it has 1 degree less than our message polynomial, as we mentioned in the math part. Okay, and then we make the commitment the same way we made the commitment for our original polynomial. And we get this number. So we create the opening triplet, this. It's just a bunch of numbers, makes no sense, but it's so cool that it's encoding a message.
Nice.
So yeah, we send this to our verifier. Now the verifier takes our numbers and evaluates this equality. So it takes the original commitment, the generator, applies it to the map, to the pairing, sorry, and evaluates this, which is basically the right-hand side of the pairing, and see what we get. True. That means we actually prove to the verifier that we know the polynomial that we claim to know. Now, the nice thing is that this is in principle sample proof, unless you know alpha. See, what if alpha is leaked? Do you remember alpha? We didn't delete it. Let's show it. Oh no, alpha is 15,754. So if a malicious party knows this number, it can take the original commitment that they know is g to the power of the polynomial and reverse it.
Interesting.
Um, Once they reversed it, they can make a false polynomial that passes through alpha, so that evaluates at the same point as our original polynomial, and the same s point, and the same in getting the same value of our polynomial on point s. Why? Because these are public, because this is our opening triplet, sorry. So this is a function that makes the false polynomial, and we get, see, such a short polynomial already fulfills our need.
Wow.
So let's do exactly the same. Let's evaluate the false polynomial on S. Let's make the proof polynomial, the false one, obviously. And let's make the opening commit and provide a false opening triplet. And let's make the false verification. See, we have the same evaluation. We have a different proof polynomial, but they don't know that because we're not going to show this proof polynomial. But when we commit, we get the same opening triplet.
Wow.
And then I asked the questions, did we deceive the system? Yes, we did. So, folks,
That's very interesting.
delete the toxic waste because you're exposing the security of the KZG Polynomial Commitment scheme. So that's it. That's an implementation. That was the math behind it
Pretty cool,
and
bro.
the math prerequisites. Any questions at this point?
I
I
mean,
don't.
I don't
See
think
the
so.
questions.
Yeah, I don't think so, but
Yeah,
it's very interesting.
it's it's hard. It's hard. The paper itself is a fantastic paper that, unless you're really familiar with cryptography, it's not so easy to read, but definitely worth doing it.
Super interesting, bro.
So yeah, I wanted to close the session mm, with a couple of open questions that can we recover the message from the polynomial? Yeah, we can actually. So I wrote this function, and you just
Awesome.
it's the message polynomial, and we get back the hello z. And question is, okay, what does our false polynomial encode? It doesn't work. I cannot decode it because it crashes. Basically it's worth nothing.
I see.
It's just used to deceive the system. Yeah, it's really evil.
Interesting.
And another thing is, okay, can we abstract this? Yeah, of course. I've written all this implementation, this example, into a class, so we can perform the same thing just with a couple comments. See, I put leak through just to not delete the alpha, and we can do exactly the same. Okay, see, the numbers are different because our finite field is different. The generator is different as well. And yeah, you can play around with it. See, we can do verify, and it applies the pairing. And again, we can do a false proof. This is our false proof polynomial. We made the commitment, the opening triplet, and verification passes.
Awesome. You're
And
gonna send this to us, this file, this document?
it's public, and I have shared it in the math channel from OpenSense.
Awesome.
Here, this is the implementation. And you can see it's basically almost copy pasting what we did in the notebook. So yeah, I'll please make sure to read the original paper. It's a fantastic paper. This one, Polynomial Commitments, revolutionary. And it also talks about more important stuff as well, like complexity. Um, see, they also have a preliminaries, the language, see, discrete logarithm assumption and stuff like that. That is very important that I didn't mention. Um, you should definitely check it out. And strong Diffie-Hellman assumption, and all the steps of the algorithm.
This is really, really
Yeah,
cool. I mean, we're definitely gonna read it.
it's a cool paper. It's tough. It's a tough one. See, we're doing actually the same, but yeah, uh, that's it on my side. And just here to answer a question. Could you please provide with some tutorials to learn from the basics? Well, depends on what you want to learn from Infinity U. In the GitHub page, which I am pasting to you right now here, I recommend reading the Moon Math Manual. I don't know if you guys are familiar with this document. It's really good book. Let's open it. These guys cover a lot of math, see, and they start similar as my prerequisites. I believe they have more examples, and see, they also use sagemath.
This is really cool.
Yeah, this book is really nice. If you're interested in the topic, make sure you read it. It gets tough. Let me tell you, it gets tough, especially here. There is elliptic curves. This chapter is hardcore,
I
but
see.
if you're passionate about it, you're gonna love it. So um, please be my guest, Infinity U, and read it out. Repo is gonna be public, and um, play around with notebooks. And if you have any questions, I believe there's the math channel here in OpenSense. I'll be having my notifications on, so whenever you have a questions, uh, I'll make sure I'll answer, or at least point you towards a resource that may help you out.
Awesome. Thank you so much, bro. That was a lot of learning. I'm quite sure that people will find this very enriching. You can find this content around. especially on video. So thank you so much, for taking your time, being here today. You always supported us a lot, and I'm really grateful for that. And yeah, thanks for your time. That was an amazing session. Unless you have anything else to say, I'm gonna close it. Okay?
Yeah, let's wait until if someone has like a couple minutes. If someone has more questions, I'll be pleased to hang
Awesome.
around